Imagine peering through a cosmic looking glass, your gaze stretching across the boundless void, landing on distant worlds orbiting suns far from our own. For decades, astronomers have dreamed of discovering lush, ocean-clad exoplanets, so-called water worlds, glimmering blue with seas that might cradle life beneath alien skies. These visions have inspired wonder, igniting our imaginations with the tantalizing hope that somewhere, out there, entire planets awash in endless oceans might harbor new forms of biology, or even civilizations gazing up at their own unfamiliar stars. Today, as we follow the winding trail of discovery, that shimmering mirage is meeting the hard edge of evidence. Are our dreams of finding ocean-covered exoplanets fading, or merely changing shape as we learn more about these strange, distant places? Let's take a journey to the heart of this new scientific debate, where centuries of cosmic speculation meet the sharp rigor of observation and simulation. The focus of this latest revelation lies with a special class of exoplanets, sub-Neptunes, worlds larger than our Earth, yet smaller than Neptune. For years, scientists believed these planets offered a prime environment for vast global oceans. The reasoning was as elegant as it was hopeful. Out beyond the so-called snow line in their planetary systems, these sub-Neptunes would sweep up plentiful ice, accumulating it as a frosty mantle. And as their orbits shifted closer to the warmth of their stars, the icy bounty could melt, filling entire planets with deep, endless seas. In the swirling chemistry of their thick, hydrogen-rich atmospheres, Hycean worlds, where hydrogen meets ocean, were thought to be born. Places where the boundaries between sea and sky blurred beneath puffy hydrogen clouds, offering a tableau as alien as it is beguiling. But just as we were beginning to revel in these possibilities, a new study is prompting us to pause, to question, to marvel anew, but in a different direction. Led by Carolyn Dorn, assistant professor of physics at ETH Zurich in Switzerland, this research has thrown a wet, if you will, blanket over the vision of ocean-choked planets. Dorn and her team have carefully crunched the numbers, delving into the hidden chemistry governing the evolution of sub-Neptunes from their fiery formative years to the cool tranquility of maturity. Their results are nothing short of paradigm shifting. Dorn's team didn't simply calculate the runaway accumulation of water. They included the way magma, that molten heart of young worlds, would interact with the thick hydrogen atmosphere. What they found was astonishing. The precious building blocks of water, hydrogen, and oxygen tend to bind tightly with metals and silicates deep within the planetary interior. The chemistry that we often imagine creating oceans in the open instead buries that water, sequestering it far beneath the surface. Even on worlds that began with an abundance of ice, the end result is a profoundly dry landscape by the time we observe them. To bring these insights into focus, Dorn's team examined 248 different model planets. The verdict was unanimous. There were simply no distant exoplanets with layers of water comprising around 50% of their mass as previously thought. The dream of Hycean planets, where 10 to 90% of an entire planet's bulk is water, fades under this new scrutiny. Instead of a cosmos dotted with water giants, what the models predicted were planets with less than 1.5% of their total mass as surface water. This is a far cry from the fantasy of endless oceans. Aaron Werlin, a collaborator in Dorn's group, described the implications with admirable clarity. The simulations show that even worlds that started out with great stores of water soon lost most of it as their chemistry evolved. The water that actually remains on the surface, in the familiar form of H2O, is limited to just a few percent at most.
Consider then the great cosmic irony. For once, it's chemistry, not just climate, that makes planets dry. The gleaming exoplanets that may first catch our eyes might not resemble Earth at all. They may be barren, their oceans locked away in mineral cages miles below the surface, or transformed by chemical reaction before they ever reach a tranquil state. Instead of sub-Neptunes glistening with water, we are presented with volatile-rich planets, swaddled in thick, impenetrable hydrogen and helium atmospheres, worlds where water, if it exists in any abundance, is either hidden in the depths or present as a fleeting trace. Nowhere did the hope for a water world burn brighter in recent memory than with the exoplanet K2-18b. Roughly 124 light-years from Earth, K2-18b made headlines around the globe when observations from the James Webb Space Telescope seemed to suggest it could be teeming with life. A team of scientists reported evidence for the presence of a biomarker, dimethyl sulfide, in its hazy, hydrogen-laden atmosphere. The prospects were exhilarating. A possible ocean world, saturated with water, was conceivably supporting not just chemistry, but perhaps even biology. But this news, so feverishly received, was met with almost immediate skepticism. Independent analyses of the same data quietly dismantled the certainty, noting that the evidence for dimethyl sulfide was weak at best. Others pointed out that even if the exoplanet possesses a thick hydrogen atmosphere, the chances of K2-18b being blanketed by an actual ocean are vanishingly small. Instead, the planet may just be another volatile-rich sub-Neptune, cloaked in a suffocating and inhospitable sky, its water so meager it could hardly support anything familiar to our sense of life. Yet as sobering as these results may be, they invite us to ponder anew the mysteries of planetary formation and the subtle wonders that reside in the chemistry of worlds. Dorn's models uncovered another fascinating twist: the few sub-Neptunes in the simulation possessing the most water-rich atmospheres were not the ones that formed far from their stars among plentiful ice. Instead, those closest in, where the planets were born amid searing heat, actually generated water chemically, as atmospheric hydrogen interacted with oxygen liberated from the molten rock below. In these hellish crucibles, water is forged not by inheritance, but by transformation. This revolution prompts us to consider an even deeper question. Might the universe's rarest treasures be found not in the most abundant places, but in those where transformation is possible? If so, then the search for habitability swings back towards smaller, rockier worlds, planets like our own Earth. Perhaps it is not the swollen, hydrogen-streaked sub-Neptunes that offer the promise of life, but rather those worlds that are kin to Earth, modest, balanced, holding on to some water but not smothered by it. These new insights cast a kind of humility over our search for life, reminding us that our own planet, with its oceans and atmosphere, may be more typical than we previously thought. It's hard not to feel a shiver of cosmic perspective as we contemplate this. Caroline Dorn herself says it gently: the Earth may not be as extraordinary as we think. In our study, at least, it appears to be a typical planet. For those who yearn for the strange and the exceptional, this may sound surprising. But there is a certain awe in knowing that perhaps our planet is woven of the same fabric as many others, its oceans, its mineral heart, its chemically balanced atmosphere a testament not to serendipity, but to the quiet, persistent laws of the cosmos. The implications stretch into the heart of planetary science and astrobiology. If Hycean worlds are likely mirages, where should we turn our telescopes next? Does the future of life searching lie among rocky super-Earths rather than gaseous sub-Neptunes? Could it be that the golden age of waterworld discovery was but a chapter, a springboard to even deeper questions about habitability and the wildly creative chemistry of planets? And still, our wonder at exoplanets like K2-18b remains undimmed. Though this world may not be a cradle of ceaseless ocean, it stands as a testament to the diversity and complexity of planetary systems that frequent our galaxy. The fact that sub-Neptunes are a class of planet completely absent from our own solar system only heightens the intrigue. What dynamic tales do they tell about the way systems arise and diverge across the span of the Milky Way? Each new finding sharpens our curiosity, challenging our theories and deepening our appreciation for the universe's endless surprises.
The story of our cosmic neighbors is far from complete. With every simulated planet, every telescopic observation, we peel back another layer of mystery. The research by Dorn and her team, published in the astrophysical journal Letters, reframes our understanding not just of water in the cosmos, but of our own place in that grand mosaic. Earth, in all its azure glory, emerges not as a remarkable fluke, but as a natural outcome of planetary processes writ large, reminding us that even as some dreams shrink, the canvas of possibility remains infinite. So, as we reflect on this chapter in our journey to map the worlds beyond our sun, let us carry our awe forward. The universe is vast enough for every twist and turn in our search for life, for every revision to our dreams of ocean planets. With each discovery, both humbling and inspiring, we are reminded exploration is a journey, not a destination. Stay with us here at Space News Network as we follow the quest, ever searching, ever learning, ever marveling at the cosmos. Because in the end, whether our dreams of ocean worlds dry up or simply evolve, the wonder of the universe is inexhaustible. Let's keep exploring together.